And we're live. So I'm going to introduce Marcelo and Vlad. This is work that took a few, is it a few years, Vlad?
Yeah,
What would you say? How many years?
couple of years.
Two,
Well, TC part almost 2 years, driver,
two
but
years.
there are
Right,
some parts in the driver that are
right.
still going on as ongoing
Hu-
projects.
Yeah, hundreds of patches. And now you get to hear all about it in 30 minutes. Okay, so with that, I'm going to start the video. And here we go.
Hello, I'm Marcelo from Red Hat.
And I'm Vlad from NVIDIA.
Um, Today we'll be talking about where turbo boosting TC flower control path has led us to with the regards of Open vSwitch. So in the first moment we'll be doing an introduction into OVS threading model and understand how it plays out with TC. We'll recapitulate TC changes we did in recent years on this matter. We'll analyze how they impacted OVS learning height and why this test is different from pure insert height tests. We'll provide a current situation and open points from TC perspective. We'll not be covering OVS specific changes. And now I'll hand over the mic to Vlad.
Okay, so here is idealized threading model for OVS. That's what we like to see when profiling the OVS running with actual traffic. So basically, OVS has two types of threads. Handler threads, they receive upcall from OVS kernel module and insert TC filters with TC filter add command. And another type of thread is Revalidator thread, which is responsible for dumping filter stats and deleting filters, either due to configuration change or aging. So why are revalidators also important and not only handlers? Because the user wants to update their statistic frequently for billing reason or just to age out short-lived flows in some deployments. So revalidators need to be able to delete at least at the same rate as handlers as well. Obviously, otherwise we would be deleting less flows than we are creating. So here is the overview of, it's a flame graph of OVS running with traffic with multiple handlers and revalidator threads. Let's zoom in to see what is actually going on inside these threads. So on the left, you can see handler threads. It's mostly spends its time in creating new filters. Besides, two other small parts are sending notifications the filter was created and calling to OVS kernel module itself. And inside the filter creation, you can see flower filter is being created and it spends most of its time uploading to driver and the in action initialization code. And on the right, you can see the revalidator threads. It mostly does dumps because during this recording, there were no deletes. So the issue that we found with TC performance during our initial analysis in 2017 when we started this project were mostly scalability issues. Initially, both classifier and action API exhibited quadratic behavior in several places. Besides that, we have an issue with parallelism. Basically, the whole TC was synchronized with one big lock, which is RTNL lock, which not only synchronizes just TC, but also multiple other subsystems. So, for example, when user tries to change like IP address on interface, it also takes RTNL logs, so it's very highly contended in systems. Another major issue was just the performance of both TC and the MLX5 driver. So it was not that fast to begin with, even without all the scalability and parallelism problems. So here is how TC really looked like when we started. As you can see, all the handler and revalidator threads contain a single RTNL lock. They're all stepping on each other's toes. And also, we are not seeing too many adds and deletes here because they take a long time. They have high latency. So let's go over what we did to solve this issue. First, scalability. So scalability, most important scalability issues was linear searches every time we tried to add a filter or action. So for example, to add a new filter, a linear search through linked list was performed in flower classifier, and for actions, it was a search in static hash table, which only had a few buckets. So on scale, it quickly degraded to just a linear search, basically. Another issue that we found that flower walk function, which you could see on previous slide with flame graph, flower walk is where DAM spends most of the time in, and before it was going through all the filters and classifier every time dump was restarted after filling previous netlink packet, which also obviously results quadratic behavior with number of filters. So these problems, they were basically programmer's dreams, textbook examples of how you can substitute slow linear time search with optimized tree lookup. And with only 4 patches, we were able to achieve significant performance improvement by substituting linear searches with ADR, which internally uses radix tree. And we are now using it for ID, filter, and action lookup. So this classifier and action lookup substitutions was performed by my teammate Chris Mee. It was one of first changes in kernel 4.14 that we made, and the flower walk optimization was done by me slightly afterwards. So parallelism issues, it's basically we were dealing with RTNL lock that allowed for zero parallelism inside TC because it was just taken before a netlink layer called TC and only released afterwards. Converting TC to fine-grained locks and atomic counters turned out to be quite a challenge. We needed to refactor the whole stack to allow parallelism. As you can see in this big list, it has taken 8 patch sets, more than 100 patches in total over the course of almost 2 years to unlock the whole stack and the MLX5 driver. So we can quickly go over these changes. I presented in details these changes on 3 previous TC workshops on previous Netdev conferences. But just as an overview, you can see that first change is RT netlink infrastructure for unlocked handlers. Before it was not possible to register a handler that does not require RTNL lock. And the following changes is actually removing the lock dependency, unlocking the action API, unlocked all actions, implementing access to lockless queue disks in classifier API, unlocking the classifier API itself is on the chains handling, blocks handling, TP handling. The only classifier we converted to unlocked execution was flower classifier, which is used by OVS to offload its flows to TC data pass. And also we needed to unlock our MLX5 driver TC layer. Before that, internally it assumed external locking, assumed there is no parallelism. So it was also quite a challenge to change everything there because we already had a lot of infrastructure implemented there. And after we were done with MLX5 driver, we needed to actually unlock TC driver callback infrastructure that glues together classifier API to driver. So again, for more details, you can check my previous talks on TC workshops. So after we done this, we get almost parallel execution. Why almost? Because initially we did not remove RTNL lock inside flow action intermediate representation infrastructure, which was upstreamed in parallel with our changes in order to allow TCF loads to be reused for net filter. We did not consider it important since flow action infrastructure code only took the log briefly to read some action data. Initial tests were done with TC in batch mode, just inserting flower filters from multiple TC instances, and they showed no log contention. So what could possibly go wrong? As you can see from the picture, AVS not just inserts filters, but revalidates them concurrently. And as you can see, it introduced significant bubbles in pipelines of handler threads, because even though they only need to obtain the log briefly, they still had to wait for Revalidator to fully fill netlink packet with filter data up to maximum netlink packet size. So this resulted significant contention when OVS was running with multiple threads. It should not have been a surprise in retrospect, but it was. So we fixed this several kernels afterwards with unlocked flow action infrastructure patch set in kernel 5.7. So with this, we were able to achieve good parallelism. As you can see on the picture, the difference with idealized representation is that dumps still need RTNL lock, but they no longer preempt adds and deletes. So it was with this change we had enough parallelism for our use case. Like maybe if some user needs to have like hundreds of these threads, maybe it will be an issue, but not according to our tests with more limited scaling. But even with these changes, we still wanted to have some more performance. Basically, we wanted to have more ads on this picture. So next were the performance changes. Here, besides TC, the major bottleneck was also MLX5 driver and its interaction with our hardware. So original approach for managing steering in MLX5 driver was to use firmware that presented unified API to driver, abstracting the difference in implementation details between different hardware generations. However, since embedded CPU, which is used to run the firmware, is significantly underpowered compared to the host, it was easily overwhelmed with high flow update rate. The problem could not be remedied with optimizations in firmware and required rethinking our approach to the way we program steering in Connectix NICs. So enter software steering. Software steering is a project that solves the issue by moving steering management to host CPU. From firmware, and it turned out to be a very big project. Right now, I counted it has like 150 something feature patches in total, and still ongoing. It tries to reach feature parity with firmware steering. And with this implemented, it allowed MLX5 to keep up with unlocked TC. And for now, we think it's good enough to be used in production. So back to TC, per CPU allocation was a major bottleneck for TC performance. It consumed up to 50% CPU in our tests. So issue with per CPU allocator were reported to maintainer of per CPU allocator and eventually fixed, but even with these fixes, it still was the biggest overhead in TC control path. Note that using per CPU memory for action stats is optimization for software TC data path. For offloaded filters, it doesn't make any sense because they don't benefit from it and only incur penalty in during action initialization and in memory usage, because per CPU memory is multiplied by every CPU in system. So no benefits, only drawbacks. To remedy this, we implemented netlink flag to completely skip per CPU action stats usage. Another major bottleneck was that dumps were too slow, even with quadratic behavior fixed. All filter and action data was dumped, even though OVS only needs stats for revalidation. So we considered several approaches for this. For example, increasing maximum netlink packet size, unlocking the dump as well to allow parallel execution, or dump less data. For us, dumpless data approach was preferable because it's more straightforward way to get a performance boost. And also OVS already had some infrastructure called ters dump that was used by other data paths. So with this, we were able to significantly improve TC performance. You will see performance in following slides. So how it is with TC now, you can see it nice pictures. We have less dumps because every dump packs more data, and the deletes and adds are fast and runs in parallel. Okay, Marcelo, take the mic.
Thank you, Vlad. And now to the test that we did. We used OpenVSwitch 215 that has support for thirst dumps and no per CPU. It's worth noting that these features are probed when OVS starts, so it will use if they are available. We used VXLAM encapsulation, which is one of the heaviest flows that we can have in terms of control path. Inside them, we had small UDP packets, because we don't want to be stressing packet switching. That's not the idea here. We used a very inner source MAC address, and the guest was running testPMD in max swap mode. With that, we can have one flow for packets that are inbound to the system and another one for packets that are outbound. So we have two data path flows per flow that T-Rex is generating. So we are stressing the control path for encapsulation and decapsulation at the same time. We used 1 million packets per second, which is enough to repeat packets often in case there are drops, and TC, OVS and TC couldn't pick it up yet, so that wouldn't impact the tests. And at the same time, it's not super heavy to overwhelm the system dealing with packets that it's not being able to learn. So it is really to try how fast it can learn, and yeah. We use it ConnectX-5 NIC. And now this is with our base kernel. It's 4.14 without RDR patches. Here we have 4 CPUs on the host. On the x-axis, we have the amount of data path flows that were learned during the test. On the left axis, y-axis, we have the total time for the test, which maps to the purple line. And on the right y-axis, we have the average insert height in flows per second. So for inserting 20,000 data path flows, it took like 25 seconds, 22 seconds, and at an average of 1,000 flows per second. Okay, so it really wasn't fast. And then we tried to scale it to 16 CPUs to get the most out of it. It doesn't scale much. It goes to 700 flows per second in the end. And the test still takes almost 50 seconds to learn 40,000 flows. And now with the IDR patches, it goes to 2,800 flows per second. And we still can see that offloading the next flow is expensive, more expensive than the previous one. With 5.4, 16 CPUs yet, with the patches to unlock TC and initial software steering. On this test, we had to bump the amount of flows in order to allow the revalidator threads to kick in. Otherwise, the test would be too short now. It's a good problem to have. Here we can still see some contention that Vlad was talking about, and this is because the flow action. The revalidators start to take longer and longer during the test, and the contention builds up. Then on 16 CPUs, it's kernel 5.5 that has the no per CPU patches. It's still some contention, but now we are at 22,000 flows per second, so quite a bump from previous one. And then the flow action unlock, which is where it made it fully unlocked. It gave 75,000 flows per second, and the graph shape is much nicer. Now the test still using 400,000 flows, and it finishes before 6 seconds. On 5.8, that has support for thirst dumps, it's not much visible on how fast it can learn, because now we can learn in parallel with the dumps. On 5.11, with a more stable software steering that has support for a buddy allocator, 7,000 flows per second. I'm not sure from which cause this jigsaw formatting there, but it gets attenuated with 5.13 kernel, 70,000 flows per second. This is 87 times faster than our base kernel. And now if we go reducing the amount of CPUs, because 16 CPUs for this in a production case is probably not a common deployment. So if we reduce to 12 CPUs, that is equivalent to minus 28% of the number of 100 threads. It goes to 54,000 flows per second on 8 CPUs, which reduces in 38% from the previous slide. We are down from 8 down to 500 threads. It goes to 32,000 flows per second. And if we go to 4 CPUs on the host, which is probably a more common deployment in production, it is minus 60% in number of handler threads from previous slide. So from 500 to just 200. It has an average of 10,000 flows per second. This is 15 times faster than the base kernel. And I'll hopefully refill your coffee because it's flowcharts time. Let's dig into where currently it is spending time when learning new flows. So this is the same slide that we had before. It has the overview. We can see the OVS 100 threads lighting up here. We can see a software AQ. We can see the revalidators, some spare CPU time there. And yes, network manager kicking in. Let's understand why. So focusing on the 100 thread, here we have the driver part, the part for the hardware floating. We have the software steering part up here. We have, for simplicity, we call TC software here, but it is the initialization of the actions. And we have the new filter notification here. FL change is from Flower. TC new filter is from the TC filters API. So the new filter belongs to it and not to Flower. And the new filter here, it represents 10% of the time that it takes to insert a new filter. The initialization of the actions takes 30% today with 513. Then the driver is taking up to 50%. So if we focus on software steering, quite on the top in there, we can see that there's a lock contention. It has the size of approximately the new filter notification, but it's actually bigger due to how mutex works. We can only see here when it's already spinning on the lock. Then moving to the handler thread on initialization of the actions, we can see IDR allocation, quite expressive here in the mirrored action. Right, most of it is just allocating IDR. We can see the peer CPU allocation being done by the destination cache that the tunnel key needs. This is for transmit. Currently there's no direct way to avoid this one. And it was nice that during this test we also noticed this. with this, we consider it an issue, and the fix is in the oven. When decapsulating TunnelKey OVS was not specifying to TunnelKey the option to not use per CPU allocations. So we kept this slide here because it's good to give an idea on how heavy per CPU allocations were when compared to like mirrored here. So if you compare to the IDR allocation that is doing here, it was quite heavy. And now to the new filter notification. There's a mostly certain reallocation that goes on when it broadcasts the notification, because TC is allocating a full SKB, and then when broadcasting it notices that it is too big and trims. And this notification, it also includes stats, which are most likely 0, right? Because we just inserted this filter. It may not be, but it's most likely. And there's this time spent carrying the driver for fresh stats. MLX5 caches it, but still needs to go there. And also collect the stats from the actions. Here it is a bit more because it was using that per CPU, but still it was 10% of the time that it took to learn. So if we could remove all these three, we are already talking about 50% of the new filter notification. But maybe we could have 100% if we can avoid this notification at all in this case. So it's an open point and it's more discussion. On the Revalidator thread, we have the RT unlock here showing up because dumping stats is not unlocked. Okay. And in this test, as Vlad was saying, we don't see the deletions going on here because there was no deletions on this test. We only stressed the inserts. And then zooming in on network manager and the handler thread to have an idea of proportions. Why network manager is showing up? It is because it receives the notifications for the new filters, and as the test stressed a lot the system, network manager couldn't keep up with the height of the messages and started losing. And it seems that after it notices that, it asks for a full dump in order to refresh its cache and make sure that it is reflecting the real state of the system. And then it starts competing with the Revalidator threads for RT unlock in order to dump the stats. So that's additional CPU use that could be avoided if we could maybe silence the new filter or make it faster somehow. So summary and conclusions. Some fixes that removed contention also sped up, like the IDR and no per CPU. The system is more stable and more scalable. It has a 15 times improvement with 4 CPUs and 87 times improvement with 16 CPUs. So it's not just add one on CPU and you have that direct proportion. OVS specific aspects were not covered here, and yet they may also help. And as we said, still some open points. IDR and Radix3 are now a considerable part of the allocation time. The peer CPU used by TunnelKey indirectly through the SD cache. If that can be avoided, it will also be helpful. The filter notifications, to at least avoid the reallocation there, it's kind of a low hanging fruit. Interaction with network manager has impacts on other parts of the system, but needs more discussion. And software steering itself. Vlad, over to you. Thanks.
Yeah, so for software steering, we considering several approaches. One approach would be to remove one big lock from software steering as well internally, but that would be trading parallelism for single thread performance. if we exchange it for several fine-grained logs, atomics, etc. Another approach we are considering is completely moving steering pipeline from host CPU and from embedded CPU just to hardware. So completely implemented in hardware that would guarantee us good performance and will remove any usage or log contention of host CPU as well. So this might be coming in future generation of Connectix hardware. Thanks, and we will be answering your questions for next 15 minutes live.
All right, thanks. Okay, well, should we let the applause go on for a bit?
Thanks.
Thank you. So let me see if there's any questions. Fantastic work is what I would say. Things take time. So if there's no questions, I'll just keep yapping here for a bit until someone shows up. So the question is, you said there were still some more patches coming, yes? What are those patches on? If I understood you correctly.
So first of all, there was a fix for OVS for the problem we found during the benchmarks that one of the cases does not send skip per CPU flag. And also we are considering how to solve the issue with software steering, because the software steering we just moved load from embedded CPU into host CPU, but we would still like to have host CPU for TC and OVS only and not to spend that much time in our drivers. So any potential implementation in hardware for steering would require adding support in MLX5 driver. Also, we're still considering what can be done about IDRs, etc. So I looked into IDR. It doesn't seem to be too many knobs to play there. So it's not clear whether or not we are really getting all the possible performance from Radix 3, and maybe we need to use something else for this.
But you already have aging in the driver, don't you? Aging already exists in the driver, if I remember correctly.
Aging with OVS is done by OVS.
Right. So your driver pulls the timestamp, puts the timestamps though. I think it pulls the hardware every X seconds or something like that.
So driver pulls hardware to cache the stats to improve the performance of TC, query, and driver for stats.
Yeah. Okay, there's still no more questions, so I can keep going. So other question is, this is not OVS specific, right? This is control plane. So any control plane could use the same features.
Yeah, yeah.
Okay.
There are people implementing their proprietary control planes based on TC.
Right. Yes, I know. Any questions from the crowd? Nothing?
People don't like flame graphs.
Look,
Too boring.
I think this is amazing work. I'm kind of surprised nobody is. Maybe, okay, let me put it this way. It's beautiful. That's why you don't have any questions. It's so perfect. Oh, and the flame graphs, from what I hear, they're great. People love them. There is one thing that you did that I wasn't very big fan of. You know, the idea to bypass, what was it, the statistics? Remember the allocation of the stats?
CPU?
The per CPU, because I wonder what happens then if, right, you only do that for the case of, I know it gave you performance, but you only do it for the sake of hardware offload. And at the end, what happens when actually your hardware needs, let's say OVS needs to pull the stats? They still get allocated in software or not?
It's even faster for OVS, because with per CPU locator, you need to combine stats from all the, it's array of memory per CPU, and it needs to combine them. But without per CPU locator, it's just integer read from structure. So it also optimizes the read itself.
Okay, so it's at the cost of maybe a little bit more memory?
It's not only cost of memory, but I assume, accessing all this memory is probably cache miss on everyone. So if you have 100 of CPUs in system, you need to access 100 slots of memory, and they probably in different cache lines, because otherwise you will introduce false sharing. So you have 100 cache misses just to pull stats for single action.
So the numbers you showed, I think Marcelo, you're showing the linear graph now. What is the current number for batching? I guess it's batching, correct? You're batching the.
No, OVS doesn't do batching.
Yeah, OVS doesn't batch.
Those were individual one TC rule per transaction.
Yeah.
What is the current number that you have? What's your best number today?
It's 70K rules per second.
70K rules per second.
Yeah, for 16 cores total. It's for VXLAN. So it will obviously depend on your profile. Here we are not cheating by using easy mode, like L2. It has tunneling here and everything.
Okay, so you are. Have you tried batching and see what kind of numbers you get? I know we have some test cases for batching, right? If you in this case, basically you have parallel threads occupying all 16 cores.
Yeah, but only 12 of them are inserted. Marcelo, am I correct? What is the computation there? Basically, part of these threads are for revalidation. They dump and delete stale flows, and other subset are for insertion. So I think in the slides
for handlers, 11, and 5 for revalidators. Because OVS does number of CPUs divided by 4 plus 1 for revalidators.
Right. But when you're running, let's say you have let's say you have 500,000 rules, right, and you do one at a time, right? You're not batching the 500 sets out of that 500,000. You can do 70,000 per second right now, correct? So that's what 1/70 times 10 to the 3. That's the transaction rate, I guess, for each one. So insertion is all the way to hardware, correct? In this case.
Yeah.
Right. So what I'm wondering is if you've tried also to do batching. Let's say you took those 500,000 and you started to batch. I thought we had a test like this in the TC test suite.
I'm not sure how much it would help these days. It would save like syscalls.
Yes, isn't that that's not a cost you're seeing in your perf output? There should be like copy from kernel user to kernel, then kernel to hardware.
Yeah, right. Definitely. I considered it some time ago, but I was hoping that maybe OVS has some existing support for batching like this. But the problem is that interaction between OVS and TC data path is basically a queue when it sends these messages one by one. So it was not trivial for me from OVS standpoint, and other bottlenecks which we described in the talk was more pressing in my opinion. But it's definitely something to consider.
Yeah, I mean, if I'm booting up my system, then I have 500,000 rules, I may consider batching them. But I understand, like at runtime, there's only one rule at a time, or maybe two at a time that show up. Then it makes sense that the transactional cost is decreased. There's a question, actually. Finally, we have a question. Okay. All right. Oops, I screwed up something. Oh, boy. Okay. The question is from Pedro. He's asking, I marked it as answered for some reason. I don't know how to answer it. The question is, how did you guys debug the contentions, the log contentions? Any tips for people trying to do the same on other areas, maybe?
Yes, so first of all, as you have seen in Flame Graph, with mutex, you can see that it's spinning. There is an optimization in mutex that if current mutex holder is on CPU, does not sleep, then any other threads that try to take the mutex, they may spin like a spin lock waiting for it to be released. So you will see it show up in the Flame Graph. And also in BPF tools, I think there is a tool that can tell you how much time thread spent sleeping, waiting for some particular lock, etc. So you can be even more precise. Like if you want to be really precise, you can combine the time it spent spinning if a user of the lock was active and sleeping waiting for the lock. But usually, if you see something spinning, then that's why Marcelo said that in reality it probably took even more time because it was also sleeping for some time.
Yeah, the RTNL lock, you mean?
Yeah, and also now it shows up for software steering because it also has a lock internally.
Okay.
So for any kind of mutex, it's a good assumption.
So parf typically will show you there's a lock, but it doesn't say which lock, right?
Yeah. But you
That's
have
right.
it, you know who called mutex locks. So unless
Okay.
you have 10 different locks in single function being taken and released, then it's probably trivial.
Okay, that's the trick. You watch which function, then you look at the code and you know which lock it is.
Yeah.
Okay, if there's no more questions, I think we're on time actually, so we can wrap it up here. There is third talk. Sorry, my brain is. I think it's Alex's talk now. So thank you. Let's give them a hand of applause here. Great
Thanks.
work. Continue the good stuff that you're doing. Thank you.
Thank you.
Thank you, everybody.